In question 3 of this series, where we learn how to measure the change of energy in a bomb calorimeter, we ended off with the following problem. The combustion of toluene has a change of energy of negative 3.91 times 10 to the power of 3 kilojoules per mole. When 1.55 grams of toluene undergoes a combustion in a bomb calorimeter, the temperature rises from 23.12 to 37.57 degrees Celsius. Find the heat capacity of the bomb calorimeter. Let's start off by writing out everything we know. We've been told delta E, and that's equal to negative 3.91 times 10 to the power of 3 kg per mole. We've been told the mass, 1.55 grams. And we've been told delta T technically by taking 37.57 and subtracting it from 23.12. Let's go ahead and use our calculator to figure that out. 37.57 minus 23.12. That gives us exactly 14.45. They are looking for the heat capacity of the bomb calorimeter, which I'll represent as C sub CAL. To do this, we need to use two very important formulas. The first one is the relationship between the heat of the reaction that's released per mole of the molecule toluene. So we have delta E is equal to QRXN divided by the number of moles of toluene. Once we find QRXN, we can use the relationship that we used in questions 1 and 2. That relationship is shown right here, where QCal is equal to C sub cal times delta T. Let's do the first step. Let's find out what QRXN is equal to. To do that, we need the molar mass of toluene, and it's equal to 92.14. 92.14 grams per mole. I'll represent that by capital M. Now if I take the mass of 1.55 and multiply it by 1 mole per 92.14 grams, this gram unit and this gram unit will go away, leaving us with the number of moles. That I can then substitute into here. Let's use our calculator. 1.55 divided by 92.14. We end up with 0.01682. 0.01682, and we stop at 3 significant figures, although I'll keep this 2 to prevent any rounding errors. Delta E was given to us in the question. It's right here. So I'll substitute that number into here. Let me show you the equation. To solve for QRXN, I multiply both sides by this number. Watch what happens. Algebraically, this goes away. And over here, we multiply it by negative 3.91 times 10 to the power of 3. The number on our screen times negative 3.91 times 10 to the power of 3. I'm going to put this in brackets just in case. This leaves us with a QRXN of negative 65.77, and that's in kilojoules. Now remember the relationship. We have the heat absorbed by the calorimeter is equal to delta T times the heat capacity of the calorimeter, and that's equal to negative QRXN, the heat released. If I substitute this number now into here, I'll end up with negative times a negative number. So we're left with 65.77 kg is equal to delta T, which I found at the very beginning, 14.45. And this is being multiplied to C. Dividing now both sides by 14.45 to solve for C, I end up with 65.77 divided by 14.45, and I end up with a heat capacity of 4.55 for this bomb calorimeter. And it's correct to the 3 significant figures that it should be. And there you have it. That is how to measure energy change in bomb calorimeters.